Welcome to the session on regression, correlation and hypothesis testing. In this session, we'll be looking at key concepts through review exercises. The objectives for this session are to review previous topics through exercises, namely, convert y equals a times b to the power x to the form log y equals a plus bx, interpret the coefficient of x in the equation y equals a plus bx, and use hypothesis tests in the context of the binomial distribution. Pause the video and have a go at these review exercises. When you are ready to view the solutions, press play. Let's solve one part A first. Given that y equals 7 times 3 to the power x, show that log y equals a plus bx, where a and b are constants to be found. So let's solve this. We have that y equals 7 times 3 to the power x. So, taking logs of both sides gives us log y equals log 7 times 3 to the power x. This equals log 7 plus log 3 to the power x. Log 3 to the power x can be expressed as x log 3, and therefore we have log y equals log 7 plus x times log 3. And this is now in the form we required. And so a equals log 7 and b equals log 3. And now for part B. For the straight line graph of x against log y, find the gradient of the line and the intercept on the vertical axis. So let's solve this. From part A, we have log y equals log 7 plus x log 3. So the intercept on the vertical axis is log 7. And the gradient of the line is log 3. Now let's take a look at review exercise 2. The average number of hours spent studying per week on mathematics, H hours, and the mark obtained in the end of year exam, M, of 30 students are recorded. The regression line of M on H is found to be M equals 33 plus 5H. Give an interpretation of the value 5 in this model. So let's solve this. If H equals 1, in other words, the student spends on average 1 hour a week studying maths, we have M equals 33 plus 5 times 1, which equals 38. If H equals 2, in other words, the student spends on average 2 hours a week studying maths, we have that M equals 33 plus 5 times 2, which equals 43. So the mark M has increased by 5. So for every extra hour H a student spends studying, they are likely to increase their end of year exam mark, M, by 5. Let's now take a look at review exercise 3. A single observation x equals 8 is taken from the distribution x distributed binomially with n equals 12, p. Test at the 15% significance level H0 such that p equals 0.3 against H1 such that p is greater than 0.3. Before we solve this, let's explore the background to this problem. So let's go back to my is my coin biased example. we've got some of the scenarios that could take place with 100 tosses on our screen. Notice that it is possible, but less likely, to get an extreme result from a fair coin. So it's possible that we have a fair coin, but it just so happens that when we toss 100 times in one go, all our tosses are heads. It's extremely unlikely, but still possible. And that is what we mean when we say that it is likely that we can get an extreme result from a fair coin. For example, these extreme situations here. In such cases, we will almost certainly say the coin is biased. Let's have a look at some theory with this example in mind. When carrying out a hypothesis test, you should be able to calculate the probability of the test statistic taking certain values given that the null hypothesis is true, including very extreme values too. The assumption for these sessions will be that the test statistic can be modeled by a binomial distribution. And the critical region is the region of the probability distribution which would lead you to reject the null hypothesis if the test statistic lands in it. So let's take a look at an example to illustrate this theory. A test statistic is modeled as being binomially distributed with n equals 12 and probability p, and a hypothesis test at the 5% level of significance uses h0 such that p is equal to 0.3 and h1 is such that p is greater than 0.3. Assuming h0 to be true, x has the following distribution. X is distributed binomially with n equals 12 and p equals 0.3. The probabilities associated with this distribution are given on the right-hand side of your screen. You can find these by either calculating using the binomial distribution probabilities, or you can look them up in your tables. Notice here we've got the probabilities from x equals 7 all the way up to x equals 12, and the probabilities associated with each of them as well. We'll notice operating at the 5% significance level as highlighted. The probability that x is greater than or equal to 7 is equal to 0.04. Notice we've added all these probabilities, and this is less than 5%. So the test statistic of 7, 8, 9, and 10 leads to a rejection of the null hypothesis. However, notice that the probability that x equals 6 is 0.08. So adding this probability to probability x greater than or equal to 7 takes it over 5%. This means that the values from 7 to 12 all lie in the critical region. So the test statistic of 6 or less would mean that the null hypothesis would be accepted. And this region here is called the acceptance region. The critical value is 7. Now let's take a look at another example. This time the scenario is very similar, except we're using the 15% significance level. Again, if we assume H0 to be true, X has the following distribution. X is distributed binomially with n equals 12 and p equal to 0.3. Here's our distribution again. Same scenario, almost, except we're using a 15% significance level. Here are our probabilities again. Notice this time, if we add up all the highlighted probabilities in the red box, then probability x greater than or equal to 6 equals 0.12, which is less than 15%. And notice we keep mentioning 15%, but this is the crucial significance level that we've been asked to use. So this time the test statistic of 6, 7, 8, 9 and 10 leads to a rejection of the null hypothesis. However, if we add probability x equals 5 to this, of course probability x equals 5 equals 0.16, and adding this to the probability x greater than or equal to 6 will take it over that crucial 15%. Therefore, this time the critical region is as highlighted. It's all those values from 6 to 12 inclusive. A test statistic of 5 or less would mean the null hypothesis would be accepted. So this here would be our acceptance region at the 15% level of significance. And this time the critical value is equal to 6. The critical value is of course the first value to fall inside the critical region. Let's now take a look at the key points again. The critical region is the region of the probability distribution which would lead you to reject the null hypothesis if the test statistic is in it. And the critical value is the first value to fall inside the critical region. We're now going to take a look at the same example, but we're going to solve it in a different way, this time by using tables. So let's remind ourselves of the example. A test statistic is modelled as b bracket 12 comma p, so binomially distributed with n equals 12 and probability p, and a hypothesis test at the 15% significance level uses H0, the null hypothesis, such that p equals 0.3, H1 such that p is greater than 0.3. Assuming H0 to be true, x has the following distribution. X is distributed binomially with n equals 12 and p equals 0.3. So let's now take a look at this. So we've highlighted the column with p equals 0.3. Notice within that column there are two values which have been highlighted in red and bold. The first of these is 0.7237. Probability x less than or equal to 4 equals 0.7237. We're going to make clear in a moment why these two particular values have been highlighted. So from this we can gather that probability x greater than or equal to 5 equals 0.2763. Notice this is greater than 15%. This is an important point. And the second value, let's have a look at this. the probability that x is less than or equal to 5 is equal to 0.8822. So therefore, the probability that x is greater than or equal to 6 equals 0.1178. And this is less than 15%. So notice this is a very critical point where probabilities go from being greater than 15% to less than 15%. And therefore, x equals 6 is the critical value and x greater than or equal to 6 is the critical region. So the probability of the test statistic falling within the critical region H0 is true is 0.1178 or 11.78%. The actual significance level of a hypothesis test is the probability of incorrectly rejecting the null hypothesis. So in other words, we're getting a very extreme result. So let's now take a look again at review exercise 3. Remember that the question stated the following. A single observation x equals 8 is taken from the distribution x distributed binomially with n equals 12 and probability p. Test at the 15% significance level H0 such that p equals 0.3 against H1 such that p is greater than 0.3. So let's solve this. From the previous analysis of this exercise, we know that x equals 6 is the critical value and x greater than or equal to 6 is the critical region. Therefore, since x equals 8 is in the critical region, we reject the null hypothesis. This brings us to the end of this session. If you have understood its contents, you should be able to convert y equals a times b to the power x to the form log y equals a plus bx, interpret the coefficient of x in the equation y equals a plus bx, and use hypothesis tests in the context of the binomial distribution. Thank you very much for listening.